So, hi and welcome everybody. In today's lecture, we will talk about some of the enabling techniques for physical layer security, and we will start with artificial noise-based physical layer security technique. So in the previous lectures, we talked about the concept of physical layer security, their categories, the merits and demerits, the enabling technologies, and their classification in different domains, time, frequency, space for adaptive transmission, artificial noise-based transmission, or channel coding. So in today's lecture, uh, we will give deep explanation of few of the enabling physical layer security techniques. And we will start with the artificial signal injection technique, where we add interference or noise in order to improve the security of our system. So as you can see in the figure over here, we have a transmitter source Alice trying to send securely a signal to the destination, and we have Eve. So what he does, he has multiple antennas here, and Alice has multiple antennas, Bob has multiple antennas, Eve has multiple antennas. So what we try to do is we try to send our signals in such a way that only the legitimate receiver can capture it. This is in blue. While in the other directions, we send artificial noise. So Eve will receive sometimes part of the signal coming from these side loops with low power, along with some artificial noise. So together they will interfere the reception at Eve, and it will prevent Eve from decoding the signal successfully. Now we will go to a research paper and explain how does this happen mathematically. So as you can see here, we have the transmitter Alice has sequence of bits. Bits at the end of the day, the bits are coming from your from the application you are using. If you are using WhatsApp, Facebook, Messenger, Telegram, whatever, at the end of the day, your messages, which are in the form of text or video or picture or audio, are converted into sequence of bits. And these bits are then modulated using any type of modulation based on the requirements of the system, using PPSK, QPSK, phase shift keying, or whatever, with different modulation order. And then the basic technique here is to add some artificial noise on top of the signal in such a way that this noise can be cancelled, can be completely removed at the legitimate receiver Bob, but it cannot be removed at Eve. Eve will get the data affected by noise, and therefore there will be some errors in the received data bits. So how does this happen mathematically? So we need to explain it directly from this recent research paper on the use of artificial noise for providing physical layer security. So here it says that most wireless secrecy communication systems consist of an Alice with NA antennas. NA antennas means the number of antennas at Alice, we denote them by NA. So if Alice has 4 antennas, then this means that NA is equal to 4. And a bob with NP antennas. NP antennas, let's say the number of antennas at bob equal 2, then NP equal 2. And an unauthorized Eve with NE antennas. If the number of antennas at Eve equal, again, let's say 2, then NE is equal to 2. This is how we represent the number of antennas at Alice, Bob, and Eve consequently. Wherein Alice wants to convey a private message to Bob under the wiretapping of passive Eve. While transmitting the information-bearing signal, Alice is able to generate specific interfering signal term called artificial noise, AN called artificial noise, so that only Eve is adversely affected by the interfering signal, while Bob remains slightly unaffected, as we just explained before. The signal that we add, which is the artificial noise, affects affects Eve but doesn't affect Bob. The transmit signal at Alice can be modeled as this. Now we will start explaining some math for you. And as you can see here, the math we are explaining is mostly dependent on linear algebra. So if you are good in linear algebra, you will understand what we are doing here. So we have information bearing signal S alone is a vector. Let me just explain S. So this is a vector, and W is a matrix, precoding matrix, and V is null space vector, and R is the artificial noise. So this S is a vector, column vector, has S1, S2. The S1 and S2 are what? Basically, they are the complex values representing the modulated symbols after the modulation step. And R here, also another vector representing what? Representing the noise that I want to convey. And this V is a matrix responsible for making the noise in the direction, in all the directions except the direction of the legitimate receiver. And W is the precoding matrix that focuses the signal in the direction of the legitimate receiver, Bob. So what does it say here? Where W, S, and VR denote the information bearing signal and artificial noise respectively, which means this is information bearing signal together, precoded, and this is the artificial noise. In practice, the precoding beamforming matrix W, this is beamforming precoding, which has dimension. The dimension of this matrix is NA by NS. NA what? NA is the number of antennas at Alice. And NS what? NS is the number of symbols inside the information vector that I want to send, which can be 2, 3, 4, whatever. So the precoding beamforming attempts to enhance the transmission quality of the information bearing vector S and denotes that the number of data stream. So NS is the number of data stream. So V, the artificial noise matrix, what's the dimension of it? It's very important to know the dimension of it because this will help us understand how the technique is working. So V is the dimension of it is the number of antennas at Alice multiplied by the difference between the number of antennas at Alice and the number of antennas at Bob. So for example, if Alice has 4 antennas and Bob has 2 antennas, then what's the dimension of V? The dimension of V is gonna be a matrix of size 4 by 2. And R, vector R is gonna be NA minus NB. Because V is multiplied by R, so the number of rows at R should equal the number of columns at V, so that you can mathematically multiply them. The transmit signal, then after that, the transmit signal is conveyed to Bob via MIMO channel H and also received by Eve via a wiretap channel. Hence, the received signal at Bob and Eve can be expressed as. Now, if I ask you, assume we have an artificial noise-based physical layer security technique that's basically used in order to provide secrecy and protect our data from being eavesdropped by a malicious eavesdropper. Could you please model or write mathematically the system model of this design? You tell me the received signal Y at Bob. Alice sends to Bob. Then the received signal at Bob is Y is equal to the channel between Alice and Bob multiplied by W, which is the precoding beamforming vector, multiplied by S vector, which is the information vector. plus H, the channel, multiplied by V, which is the null space vector that's responsible for aligning the artificial noise in the direction of Eve, multiplied by R, which is the random noise vector that I will put, the random noise values that I will put inside the vector to affect Eve, plus U. U is a Gaussian, a complex additive white Gaussian noise with elements obeying IID. Okay, and Z, the received signal at Eve. At Eve, also Eve wants to receive the signal, has a channel G. So G, the channel, is a matrix. Also, the dimension of it is the number of antennas at Eve multiplied by the number of antennas at Alice, multiplied by WS, which is what the transmitter Alice sends, plus G, the same channel, multiplied by VR, which is the noise added at the transmitter, plus V, which is the additive white Gaussian noise at Eve. Now, how can I add the noise in such a way that it's orthogonal to Bob reception? If it's orthogonal to Bob's reception, in this case, what happens? If it's orthogonal to Bob's reception, Bob will not get affected by the artificial noise interference, but Eve is the only receiver that will get affected by the noise added at the transmitter. So with the channel state information of Bob, an orthogonal artificial noise can be conducted using null space projection, specifically assuming V is the null space of H, HV equals 0, the influence of AN can be mitigated at Bob as follows. So if I told you V is the null space of H, means the vectors inside V are orthogonal to the channel between Alice and Bob. And when the channel, mathematically, if you multiply something orthogonal with another thing that's orthogonal to it, the result will be completely zero. And therefore, the interference at Bob will cancel and become zero. So if H multiplied by V here zero, then the whole term will disappear. The whole term will go away. And the net received signal will become Y equal HWS plus U. Now, how do you find V that will make HV equal 0? That will satisfy this condition. How can you find it? We find it using an algorithm that you maybe heard about it or studied it in the linear algebra course called singular value decomposition. Singular value decomposition is a mathematical technique that allows us to find the eigenvectors and the eigenvalues of a certain matrix. And consequently, we can determine the null space of that matrix. The null space is the orthogonal vectors that if we transmit in their direction at the receiver side, they will fade away, they will go away. They will disappear, basically. So you put something at the transmitter, but by the time it reaches the receiver, after it passes through the channel, it will disappear. This is like magic. So H, if you apply singular value decomposition on the channel matrix between Alice and Bob called H, then the result will be U, D, V1, V, Hermitian. So U is a matrix, a unitary matrix composed of left singular vectors of H. Left singular vectors, they are independent vectors. And the dimension of this matrix that contains these vectors is NB by NB, which is the number of antennas at Bob. If Bob has 4 antennas, then the dimension of U will be 4 by 4. And D represents a diagonal matrix whose entries are the singular values. So we have eigenvectors and we have eigenvalues or singular values of it. And the dimension of it is NB by NB, which is the full, we call them the non-null. We have null space and non-null space. So these are the non-null space eigenvalues. And V1 consists of the first NP right singular vectors of H, which is NB by NB, NA by NB, spanning the subspace corresponding to the information bearing signal, and V is the null space which has a dimension of NA by multiplied by NA minus NB. So at the end of the day, we can obtain the V, the null space vector, which can also be calculated using this formula. I is the identity matrix minus H Hermitian multiplied by H Hermitian all inverse multiplied by H. So that's basically how the techniques work. This is how the artificial noise technique functions on the mathematical level. So let's return back to the slides. Any questions about this technique and how it works so far? Everything is clear, I assume, if there are no questions. So this is regarding the artificial noise injection in MIMO systems. But there is one condition that we need to pay attention to. There is one important condition that we have to make sure that it's satisfied when we are using this technique, which is that the number of antennas at the transmitter Alice should be greater than the number of antennas at the receiver Bob. If the number of antennas at Alice is not greater than the number of antennas at Bob, in this case, we cannot apply this technique. Why? Anybody can tell you why? Why cannot we apply it if the number of antennas at Alice and Bob is the same, for example? Because in this case, mathematically, there is no null space. To have null space vectors, you have to have a degree of freedom. A degree of freedom means more antennas at Alice than the number of antennas at Bob. So this extra degree of freedom can create the opportunity of having null space vectors that can be used in order to what? In order to send the artificial noise signal that affects Eve but doesn't affect Bob. Good. So in case we don't have what? Let's say we don't have in case we don't have null space in our channel, what can we do? Anybody can tell me what can we do? We have techniques that don't depend on using the null space in the channel. Even if we don't have null space, we can still send artificial noise, but these techniques work in a different way. So for example, this technique called ARQ, adding artificial noise by exploiting ARQ. So in this technique, we have the transmitter and receiver Alice, and the transmitter in the first round sends the signal, this signal X, with an artificial noise on top of it. And when it goes to the receiver, whether Alice, whether Bob or Eve, they will not be able to decode the signal successfully because what? Because it got interference, and this interference is not in the null space, so it cannot be removed. But what Bob does here at this side, it saves it, stores it in its memory, in its buffer, and then requests another retransmission of the same packet. In the second round, what Alice does, sends the same signal that he sends in the first round, but with an interference signal that can cancel the first interference signal that was added to the first packet. Only when Bob applies maximum ratio combination at its side. because the maximum ratio combination here uses the channel, Bob's channel. In this case, the combination is function of the channel between Alice and Bob, and the channel is this channel is completely different from the channel between Alice and Eve. Therefore, the net received signal after doing this manipulation and this maximum ratio combination will become the signal itself multiplied by the channel, which is basically what I suppose to see when I'm sending my data without any noise. So my data is pure, clean, clear. All what I need here is to get rid of the fading H1 and H2 by dividing over them, and I will be left off with the data itself. So this is one of the technique as well. And in case, what's the problem with this technique? This technique, it's good that it can allow you to provide security even when you don't have null space, which means the number of antennas at the transmitter are the same as the number of antennas at the receiver. But there are cases where I don't want my transmitter to retransmit each packet 2 times because this can degrade or reduce throughput in the system. Yes? If you, for each and every packet, instead of sending it in 10 seconds, you are sending it in 20 seconds, what will happen in this case? You will reduce the internet speed by half. So this is not good in this sense. Of course, it can provide me good, excellent security, but if each and every packet I want to send it twice, and I need to wait for it double the time, this can reduce the throughput, can cause more delay. And therefore, in an environment where I need a higher internet speed, this might not be an ideal technique to go with. So what I do in this case, I can select another technique. This technique, for example, called OFDM with artificial noise injection. So we assume here that we have a system where it has 2 antennas and it works regardless of the number of antennas at Eve or Bob. You can add as many antennas as possible as you want, but for now, for simplicity, we assume we have 2 antennas at the transmitter, 1 antenna at Bob, 1 antenna at Eve. So in this case, we have the data bits that we want to send, and then we modulate them. And the same data bits, we send them from 2 different antennas located at 2 different locations. And here in the frequency domain, before the I50 process, we add an artificial noise signal called R1. And then we pass them together to the I50, and then we add CB and pass them finally to the antenna. And the antenna converts the current into electromagnetic waves, and the electromagnetic waves get captured and at Bob's antenna, and the electromagnetic waves are we basically deduct the current from these electromagnetic waves at Bob antenna, and this goes as an electrical signal. And then we start processing this signal by removing the CB, then passing it through FFT, fast Fourier transform, which is a mathematical technique that can convert signal from its time domain to the frequency domain because it's easier to process the signal in the frequency domain. And then equalizer to remove the effect of the channel. Then we demodulate the symbols, and finally we receive the bits. So how does this technique work mathematically? So here at this point, we add artificial noise signal, which is basically a random vector A divided by the channel between Alice and Bob, H1. And then for this branch, we also add artificial noise signal R2, which is basically also a random signal A, but divided by the channel between transmit antenna 2 and Bob, which is H2. and this is a diagonal matrix in a diagonal matrix in the frequency domain. So the received signal at pop from antenna 1 will be equal to h1 is the channel between them multiplied by x plus a over vector h1, and y2 is equal to h2 multiplied by x minus a over vector h2. Okay, so now these, when you add them, they will reach pop and they will add to each other. After you pass them through these blocks, at this point exactly, this term and this term, they will cancel each other, and you will be left off with just h1 plus h2 multiplied by x. In this figure, just like this value, but this is in time domain, here in frequency domain. So this is one of the techniques that we use in order to provide security when we don't have null space. We don't necessarily need to have null space, or we don't need to retransmit the same packet twice. So these are the techniques, the 1, 2, 3, and the next technique after that, if we don't want to transmit our signal from the same transmitter, we can have two transmitters but synchronized with each other, two base stations. And these base stations one of them can send the signal to Bob, and another can send the same signal again to Bob. But one of them adds R1 and cancels it, the other one R2, in such a way that when they reach the receiver, they get canceled out. R1 can be A of n over HB, R2 can be A of n over HB2, and the received signal noise can be something like that, an function of noise, and its function of the signal to noise ratio. So in this case, the received signal from the first base station is this, and from the second base station is this. And when you add them together using so they add together, basically you add the first signal plus the second signal plus noise, you end up having this signal xn plus noise over the fading channel. But for Eve, because the signal is function of Bob's channel, he will not be able to cancel them when he adds the signal from the first base station with the signal from the second base station. As you can see here, they will not cancel each other, and therefore you will still receive noise and interference at Eve, and therefore Eve will not be able to decode the signal successfully. So we can have a break here, and we continue after 5 minutes. Thank you.